Vinod, thank you very much for having me here today. So I'd like to invite all of you to just type in questions or ask questions during my talk. I can certainly skip some later slides, and just I think having a conversation is more interesting than having me just deliver the talk to myself. And so I should say, make a disclaimer at the very beginning. It's still very speculative to consider these new material system for quantum information science. So for the last few slides, I'll share my idea, how they can be used for that purpose. Okay, so let me, first of all, thank the people who did all the hard work. And this is an older picture of my group now, perhaps taken 3 years ago. And I think one of the gentlemen is now at your institute, doing PhD studies. And the work that I'm going to share are mostly done by my graduate student and postdoc. Some of them are actually from collaborators group. And these are my, the bolded names are my key collaborator for the work I'm going to share with you today. So one way to kind of put a framework for a lot of our project is we want to contribute to information technology in general. And if you think about the current information technology, quantum physics already play a major role. So we do information storage in magnetic thin film with these tiny domains. The domain size already on the order of 10 nanometer. There's a challenge to keep shrinking these domain size, and thermal energy will cause instability as we keep on going to smaller size domains. And of course, everybody here knows that the information processing is on silicon transistor, and the channel length between the source and drain in silicon transistor is already down to 7 nanometer, and there are plans to go down to 5 nanometer, perhaps 3 nanometer. And if you think about an atom is about 0.2 nanometer in diameter, we're not left with many atoms between the channels. So certainly the silicon-based technology will saturate at some point. It's already slowed down compared to the doubling of the density every 2 years, described by the Moore's law. So one thing about transistor is when you make the channel length shorter, you also want to make the material thinner. So you want to keep some aspect ratio. And that's why there are companies that have already seriously started to look into this atomically thin semiconductor that I'm going to tell you today. So we're not just doing things that are of academic interest. They could actually make an impact in technology as well. So we all know, magnetism is highly quantum mechanical. We don't have as a very correlated system, we don't have a full grasp of these magnetic material. And then transistors, even today rely on the quantum tunneling phenomena, and it's completely a quantum phenomena. Information transfer for the bulk part are done classically by light, confined in these optical fibers, but there are quantum communication protocols that are relying on single photon sources or entangled photon pairs. And there are a lot to do still to improve those technologies. So as a physicist, if we were to make a prediction what come next for information technology, we're all very confident need to take another quantum leap in the sense we need to work with smaller devices, learn how to operate them faster, and doing so in an energy saving way. So my group and many others in the physics department don't work on devices that are going to be on the market. We ask these basic questions. And what are the smallest objects we can use to store information? And how do we communicate information via the smallest pocket of energy and the single photons? And how fast can we manipulate such information that are encoded perhaps in single electrons or single holes? And to understand these, to push the limit on these questions, we also need to define, first of all, how small is small and how fast is fast. A big part of my group are devoted to understand quantum coherence associated with the electrons using ultra-fast spectroscopy, but I won't have time to go into those spectroscopy studies. Instead, I'll focus on how small is small today and showing you what are the possible way to start storing information, perhaps in a checkerboard array of electrons or holes, and also manipulate them on a level or gain single photon emissions on the level of individual excitons. So that's what my talk is going to focus on today. And so we can ask, how do we achieve these ultra small devices? And a solution that we've been playing with for 3 decades, at least or close to 4 decades now, is what we call the quantum confinement. So you take a bulk material where electrons can move in all 3 dimensions. If you can somehow thin down the dimension, thin down 1 dimension and confine the electron motion in a 2-dimensional plane, you have created what we call the quantum well. And high-speed transistors made of gallium arsenides are relying on these quantum wells already. And if you can find strategy to further confine electron motion in 1 dimension, you created what we call quantum wire. And when you confine the electron motion in all 3 dimensions, you created what we call quantum dots. Perhaps this similar, like a natural place to ask, can we use quantum dot, the smallest droplet of semiconductor, that perhaps used to confine individual electrons or holes for information storage and processing. And for those of us, who have, the students audience, if you have completed introductory solid state physics course, you understand why you are, electrons are not allowed to occupy any energy states. In atoms, they have these discrete energy levels. In solids, they occupy bands. In semiconductors, they have full valence band and empty conduction bands. As you change the dimension of the electron motion, you're shaping the allowed energy state. You're shaping the density state. So by changing the dimension of the electron motion, you're really modifying the material property in a very fundamental way. And for our studies that mostly deal with optical property, you're changing the light emission colors and also the statistics of how lights are emitted from these quantum materials. And here, so you take a rubber ball, make it smaller. You just got a smaller rubber ball. You need to squeeze them so tight to really get to the quantum limit. So this is a type of quantum dot we call colloidal quantum dot made in solution. And here, these are solutions with a lot of semiconductor droplets suspended in them. And the core size of the semiconductor droplet varies from about 6 nanometer to 4.5 nanometer, and you have already tuned the emission color through the rainbow color. And there are actually quantum dot TV you can buy on the markets. Take advantage of this, very convenient way to shape the color of the light emission through just changing the quantum box where the dimension where the electrons are confined. So in terms of a 2D material, many of you probably are already tired of hearing this. We are in the era of atomically thin material. These 2 gentlemen was given Nobel Prize only 5 years after they published a seminal paper in which they show there are many different materials that you can actually simply use a Scotch tape to thin them down to atomic layer thickness. Because these materials are layered to begin with, within the 2-dimensional plane, the atoms are bounded by strong covalent bond and ionic bond, but between the planes, they're bound by weak van der Waals forces. So we've all heard a lot about graphene or stacked bilayer graphene that isolated from graphite. I'm going to talk about the semiconductors that this is transition metal dicogenite. And you can also exfoliate these complex cuprates materials, and they also have layer structures. And this is another example that can exhibit very rich quantum phases. So because you can already thin down the material to a single unit cell thickness, these materials represent the ultimate limit in 2-dimensional materials. So these will be the building block of Moiré superlattice I'll talk about shortly. And the main material I'm talking about is a semiconductor that I'm just going to refer them to as TMDs. Basically, it's a layer of transition metal that are sandwiched between 2 layers of chalcogenate atoms. And if you take a top down at these lattices, you would also have their honeycomb lattice with AB lattice site occupied by different atoms. In graphene, for example, you also have AB lattice, except for they're made of single atom carbon. But just the fact we have to deal with 2 atoms already make these materials difficult to control from a growth point of view, because these 2 different atoms have different vapor pressures and temperatures, make them difficult to create a perfect material. But nevertheless, when you exfoliate them from a bulk, there's literally no dangling bounds. So that makes them a really nice building block for various electronics and photonic devices. But I should say they're far from ideal. We often have vacancies, that are generated in the growth of these materials. And people mostly work with materials that are created two ways. One is created by what's called the chemical vapor deposition. And these days, people can grow full wafer of TMD materials with large flake size. And mechanically exfoliated sample can also be as large as 100 microns or even bigger. One of the very compelling things for people study optical property of this material is that even from 2-layer to a single layer, the optical spectrum changes dramatically. So in a single layer, you have these very sharp emission that pop up with emission intensity more than factor of 100 larger than a bilayer. So the reason for that very dramatic change in optical property is related to their band structure. And I should also say this resonance is what we call exciton resonance. So I'll just give you a minute introduction of what's an exciton. As already mentioned earlier, in semiconductor, you would have a full conduction bands and full valence band and empty conduction band. You need to provide, if you want to excite the material optically, you need to provide enough energy, and so you can promote the electron from the valence band to the conduction band. When you do that, you left behind what's called a hole that has a positive charge. Hole is a missing electron. So this electron and a hole are bound to each other through Coulomb force. And in this atomically thin material, the binding energy is very strong, on the order of 200 or even higher MeV, compared to thermal energy at room temperature. Thermal energy at room temperature is 25 MeV. So these electron hole pairs are stable even at room temperature. So also it's important to appreciate there are two types of semiconductors, and one is called direct gap and one is called indirect gap. So what I'm drawing here is a dispersion curve. The x-axis is the quasi-momentum in the crystal, and it has a Brillouin zone, the range that you need to describe the electron band structure in solid. The size of the Brillouin zone is pi over A. A is the lattice constant, and it will be 0.2 nanometer approximately. But then when you shine photon on the material, photon has a wavelength on the order of 500 nanometer. So in the scheme of the Brillouin zone, photon carry a very small momentum. So typically light absorption and the light emission is what we call the vertical transition, meaning the electron and hole involved in the optical absorption process literally have the same crystal momentum. And that makes the direct semiconductor much more efficient in absorbing and emitting light. If you do have an indirect gap semiconductor, meaning the bottom of the conduction band happen at a different place in the Brillouin zone compared to the top of the valence band, this transition needs assistance from another quasi-particle to provide the momentum, oftentimes a phonon, and that process becomes much more inefficient. And so this is the reason why when I move from bulk to a mono, even from bilayer to monolayer in TMD, it made a huge difference in its optical transition. So I'll just acknowledge these plots are messy to me as well. They look like just messy spaghettis to me, but we only need to pay attention to these red noodles and blue noodles. So this is the bulk band structure, 4-layer, 2-layer, and the monolayer. As you can see, the top of the valence band in the entire Brillouin zone is not lined up with the bottom of the conduction band in the bulk material. And they're not lined up until you're all the way down to the monolayer limit. So that's why from a bilayer to monolayer, you actually have a fundamental change in the band structure. And when it becomes a direct gas semiconductor, that light emission becomes 100 times or even more efficient. Another property for this material is these excitons actually happen at the boundary of the Brillouin zone. So there are the Brillouin zone is also hexagonal in these hexagonal lattice, two-dimensional lattices, and there are two inequivalent bodies. So I'm going to call them K and K prime, and they're related by what's called the time reversal symmetry. And in the in the context of my talk, it basically means if I have an electron with spin up in one valley, I can always find an energetically degenerate bands in the opposite valley with the opposite spin orientation. Therefore, I have exciton transitions that follow different selection rules and that are excited by photon or emit photon with different helicity in K and K prime valley. So now this is a binary degrees of freedom, and people start to speculate. You can use this, what's called the valley degrees of freedom for information processing. For any two binary degrees of freedom, I can draw a block vectors. And if I have electron hole or pair of excitons in one valley, I call that 0. If I somehow manage to move it to the opposite valley, I call it 1. So I can follow the quantum dynamics of between these valley degrees of freedoms. So this is another thing that's unique about these materials, that the exciton transition happened at a boundary of the Brillouin zone, and there's a 2 copy of it. So people have come to appreciate, besides a single electron hole pair, there are other transitions that are important in this material. So here is one that's called trion. Basically, if the semiconductor is doped, you create an electron hole pair optically, for example, and they will actually bound to an extra hole or extra electron, make this a 3-particle bound state that's called trion. And they can also bound with another pair of excitons, form a biexciton. And it turns out each of these quasi-particle has unique properties in the context of quantum information science. So if I can isolate a single exciton, they will act like single photon emitters. If I can work with a single trion, it's a great way to realize spin photon entanglement or to transduce information between photon and the spins. And a biexciton is a great way to create entangled photon pairs. These quasi-particles have all been studied in traditional semiconductor, quantum Waals, and quantum dot, for example, in indium gallium arsenide, except for the binding energy for these quasi-particles is about 10 or even 100 times bigger than their conventional semiconductor counterpart. For one reason is the Coulomb field, the bounce electron hole pair, can now extend outside the 2D material. They're not screened, and making the binding energy stronger. And as I mentioned already, the binding energy can be, for the exciton, for example, is on the order of 200 MeV, make them absolutely stable at room temperature. So making a lot of this phenomena that now can be explored at room temperature. If you have a more heavily doped semiconductor, you actually need to worry about new type of optical excitations, but I will skip this for the purpose of today's talk. So this is my 10 minutes, 15 minutes introduction to these atomically thin material. I want to pause briefly to see if there's any questions. Then I'm going to launch into Moiré superlattice, which is the core of the talk today.
Elaine, I don't see any questions in the chat. So I guess we are good to go.
All right. Okay, so my own group and many others have started to move beyond to study a single monolayer semiconductor. Many of us have learned to stack 2 monolayers together vertically, and then also doing so in a controlled manner to control the relative twist angle between the 2 layers. As you can see, there is an in-plane superlattice that develops that we call Moiré superlattice, and the size of this unit cell is controllable. The bigger the twist angle, the smaller the supercell. My hypothesis going forward to introduce them as a platform for quantum emitters and for quantum information science is that these quantum boxes have now allowed me to define an array of regular quantum dots. Okay, so I started with 2-dimensional material. Now with a twist, I argue now we have an array of quantum dots. Regular space with sufficient confinement energy. So I get, this is the outline of the technical content. Maybe I only get to go through, one half of it, but that's okay. It's going to get more complicated. Again, feel free to stop me anytime to ask a question. So my understanding of these materials started, from the STM, scanning tunneling microscopy experiment that my colleague does at UT. So this particular material is actually chemically grown. So in this particular combination, the chalcogenate atoms are different. And therefore, the lattice constant for these two composite, this two monolayer differ by about 4%. These materials are actually rotationally aligned. There's no twist angle. When you grow them, the energetic is such that they tend to be rotationally aligned. Okay? Even though there's no twist angle, because the lattice constant differ by about 4%, I can move from one position in the Moiré supercell over by tens of an atomic unit cell, I would have a different atomic alignment. So there are about three high symmetry points that would call AA side, and the AB selenium side, and AB constant side, which just refers to different atoms sticking out in the center of the hexagonal or the top layer. The details doesn't matter too much for the purpose of my talk today. But these 3 points, these 3 points are actually all follow threefold rotational symmetry. So they're special in that sense. So these images are topology. It says actually the layer spacing are actually changing as you change the atomic alignment. And this particular picture, I can search, this could be topology, or it can actually be a mapping of electron density. So if I take a STM tip and I can start injecting electrons into this 2D material, they will find their spatial location where electrons tend to puddle up. Okay. So I want to be clear, these are not optical measurement. In optical measurement, we do not have such spatial resolution, but it certainly informed how I imagine this material would behave optically. So the existence of the Moiré superlattice has been confirmed by many imaging techniques, and this is the highest resolution. TM images, you can literally see the top and bottom atoms are gradually shifting in their alignment. Again, here's a simulation, here's the experiment. What's more powerful is what my colleague did is to measure the band structure, local band structure. So let's only focus on the bottom panel, and they basically measure the band gap at few selected points. These 3 points are the point that with threefold rotational symmetry. And you can see the measurement have showed you local band structure changed by almost 20%, or 200 MeV. This is measurement, and this is calculation. Calculation done by DFT calculation are not expected to match the experiment in absolute value, because their fundamental challenge is to define what band gap is in those calculations. Important thing is they also replicated this trend, how the local band structure changed from one point to the next. And the amount of change is very similar to the experimentally measured value. So this gives us confidence. You actually have these potential traps that would serve to localize electron and hole or electron-hole pairs. The localization of this carrier can also be looked at from band point of view. You also have very flat bands. When you start to introduce the Moiré supercell, you start to fold the Brillouin zones. You have Moiré mini bands. They turn out to be very flat in these TMDs. The reason for flat band is different in TMD bilayers and graphene bilayers, but so there's plenty of experiments that already directly map those flat bands as well.
So Elaine?
Yeah, please.
So when you have these two, especially the sulfide and the selenides on top of each other and the lattice constant not being same, is there a strain component that comes into picture?
Yeah, good question. So I'm not sure how much strain is there that in the grown area that's no distortion. So, certainly if they also grow these, they have lateral heterostructures, and near the interface regions, you would actually see strain, but they also typically cause distortion of the moire. Mm-hmm. So people were able to image the distorted moire and figure out how much strain there is. But also come back and say, we know there's strain. Some are very intrinsic, how strain would modify this simple picture I just presented to you can vary, depends on the twist angle. Okay, so so I'll maybe I'll get to that later today. So there are definitely strain, either intrinsic or extrinsic in the Moiré superlattices. Okay,
can I ask a question as well?
please.
So when you go across the domain wall, which separates the AA and ABST, for example, the gap varies uniformly?
So, I guess there isn't so much a clear domain wall in this picture, but we know there are lattice reconstructions and the triangular lattices, and there's more clear domain and domain walls. I guess what I'm saying is if you have different atomic stacking, you will have different band structure, different band gap.
Okay, so the excitations are not localized, but they do form a band across.
Whether or not you always have bands, you still have semiconductors, right? But the semiconductor band gap is changing, depends on whether you are here in the Moiré supercell or there in the Moiré supercell. That changes.
Okay.
Okay.
Okay, thank you.
All right. So there are still semiconductors, the band gap exists is very well defined, but it's quickly varying within the Moiré supercell. One way to think about this, we all know semiconductor band structure calculations start with tight binding model, right? You're really reconstructing those electron orbitals from the atomic orbitals to start with. And if you have a different atomic alignment, the wave function hybridizations are different, and it will cause different bands locally. So that's at least a kind of a qualitative, simplistic picture I use to help myself to appreciate why there's a band gap variations in this Moiré supercell. Okay. Other questions before I go on? Okay, hopefully I talk a little bit about how band structure changes. And now let me talk about optical property. And let me warn you, I've already shifted the material combination. Okay, so this time, a lot of the results in my group are done by mechanically stacked samples, and I'm going to use a combination just because the optical spectrum is very clean in these combinations. So I'm using MOSC2 and WSC2. In this case, the Caucasian atom is the same. The lattice constant is very similar. And then when you stack two semiconductors together, you also have to ask yourself, how does the band shift relative to each other? That's a band alignment. For any semiconductor heterostructure, you have to answer that question experimentally. So many experiment has pointed to this vertical heterostructure has what's called a type 2 band alignment. That's a jargon. What I really want to say is the electron would tend to go to one layer and the hole will tend to go to the other layer. One of my undergraduate taught me to think about the holes as the bubbles in your soft drinks, and they just flow up. Okay, so and then as soon as you create carriers, either electrically or optically, electron would tend to go to one layer and the hole will bubble up to the other layer. And now, in addition to these electron hole pairs that you can have within the monolayer, you would have this electron hole pair that can be in opposite layers. These two species of excitons will both experience the Moiré superlattice, but they have very different properties. These intralayer excitons have huge dipole moment, very short lifetime. The interlayer excitons has much reduced dipole moment, much longer lifetime. As we learned, we can actually control the lifetime of this interlayer exciton very easily by the twist angle, by a factor of 10 easily, much longer if we explore much bigger if we explore a bigger range of twist angle. So their property are very different. Their energy also very different. Largely, if I assume the binding energy is the same, the interlayer exciton would appear at lower energy because the band alignment has shifted. So you can see this transition are going through a smaller energy gap between them. Another complication is that not only these Moiré supercell impose energy modulation, they also impose optical selection rule modulation. So remember, I talked about K and the K prime value in the monolayer. That concept still holds. I still have 2 copies of excitons that would have time reversal symmetry relation between the 2. But if I only follow one value, if I just say, what is my transition in the K value in the heterobilayer, I have another variations. So if these transitions are drawn in the K value alone, just know that will have energetically degenerate transitions in K prime value that will follow the opposite helicity. Okay, my apologies that I keep changing notation on you because we've been changing notations in our paper just to be in line with some of the theory paper we've been following. So a lot of these optical transition selection rule changes was first proposed in this paper by Xiaoqin. So if I were able to put electron hole pair in one location versus the other location, these are the 3 high symmetry points that I previously called AA, AB, W, ABM, that notation. If I were able to put them in different location, I would have sigma minus a sigma plus transition in one location and sigma minus transition in the other location. In the 3rd high symmetry point, I would actually have a dipole moment that's perpendicular to the plane and do not easily couple to the plane wave. So that is to say, not only I have this energy modulation in the Moiré superlattice, I also have optical selection rule spatial modulation in the Moiré superlattice. And they couple to different chiral photons. And as people in photonics know, of course, you can use chirality of the photon to encode information, right? So basically, we would have a checkerboard array of quantum dots and with different helicity that's hosted in this Moiré supercell. But these, the Moiré supercell, when we stack them together, if I stack them with 1 degree twist angle, the lateral dimensions of the Moiré supercell is on the order of 20 nanometer. And the old experiment I'm going to show you now are done in far field, meaning I'm coming down with a laser spot size that's about a micron. And I'm covering 500, 1000 Moiré supercell. And they're not perfect. Okay, actually, when you grow them with CVD, the structural periodicity is more intact. But the downside of the CVD samples, they have high defect density, then the resonance are broad, and that will mask the quantized states that we can uncover using the stack sample. Okay, so we don't choose to stack samples if we don't have to do it. We want to avoid doing it, but unfortunately, at this point, the mechanically stacked samples still give us higher quality optical spectrons. That's why we do it. Okay, again, let me pause and see if there are questions. This is also another very important part of the talk that, as you can see in the bilayers, there's a lot more complexity that are introduced to the optical properties.
So the excitons are localized.
That's a hypothesis.
Okay.
I hope to prove to you that they can be localized. They may not be. So there's some condition you want to satisfy. Okay.
But if you have different selection rules in different regions, and if you created an exciton in one region, it cannot tunnel into the other.
Yeah, so there's another picture that can also introduce selection rule variations for excitons in this. So this is the first picture that we use to guide our thinking. But then I'll talk about that shortly. Okay, so this is one possibility that you have these checkerboard emitters with different selection rules. But you have to ask, is the potential trap deep enough, right? So the electron in a hole, if you ask what is the minimal of the conduction band and what is the minimal of the valence band, they may not even show up at the same spatial locations in the Moiré supercell. There are a lot of complexity that can emerge. I'm not going to go into all those complexity, partially because our optical experiments are not specific enough to confirm it one way or another. Okay, so there's still a lot of things to be understood. We're just starting to scratch the surface.
Okay.
Questions?
Yeah, I don't see any more questions.
Hi, Elaine. Just I have one question. So, so in this interlayer excitons, the excitons forming between the upper layer and bottom layer. So in this case, the dipole moment seems to be vertical. So is it possible to excite this one with the normal incidence and the plane wave excitation?
Yeah. So so this is a simplified picture. Most of the time, there may be some spatial extension for the whole wave functions that are permeated through the other layer as well. So, I think this is just a cartoon picture that's not 100% accurate. So, certainly we see the emission from them very, very easily. The absorption is very weak. So people cannot do direct optical absorption, see this resonance because their dipole moment is much smaller than the intralayer excitons. So this is cartoon.
Yeah.
And also,
sorry, go ahead.
So
No,
I guess what I'm trying to say, we do not use photon resonant with the interlayer exciton to directly resonantly excite that dipole. Typically, we put carrier into above the gap, or you can directly create an intralayer exciton. And then because of band alignment, they're going to be charge transfer and then form the interlayer exciton. And then they can recombine.
Okay, thank you.
Elaine, there's a question in the chat from Oleg Berman. He said, how does the feature of twisting TMDC bilayer improve the possibility of information applications compared with TMDC monolayers?
Right. So, in TMDC monolayers, first of all, I have this one, I don't have a way to define my unit cell. Right. I have the electron hole or the exciton just moving in two-dimensional plane. Now I take that system and twist it. I actually define this quantum boxes, which I could use to encode information with either electron spin or hole spin or electron hole pair.
Actually, I thought that based on what you said, like maybe 15 minutes ago, that the possibility of applications for TMDC monolayers for quantum information is based on the fact that there are two values. And when we have exciton electron hole recombination in exciton, we could have circularly polarized light in different polarization, and entanglement between different values could provide a qubit. So now we have it twisted, we can localize it.
Yeah.
But in which way that would be good for information?
Right. So first of all, I think that when people were first paying attention to the value degrees of freedom in this material, what you just said is the thinking starting around 10 years ago. So there's a lot of work that's shown in the monolayer, the value degrees of freedom, especially associated with the optical transitions, it's actually not that long-lived. And then, now with the twisted bilayer, you have a real space defined, quantum boxes. By the way, the value binary degrees of freedom is still there. So basically, if I just look at the exciton in this one location at AA, for example, I still retain that binary degrees of freedom. The question is how long-lived they are, how can you control them? But now I don't rely on these carriers that are free to move around in two-dimensional plane. Instead, I find another way to confine their motions in all three dimensions. But so far, I have not proved to you that they're necessarily localized.
Oh, I see. So, but still the binary degree of freedom 0, 1 means one value or another value.
Correct. You can still use value as a binary degrees of freedom to encode information.
Mhm. But that you have it located somewhere, that makes it kind of more simple to measure this recombination, like photons from recombination. Is that true?
They're not simple to measure. It just I have created a checkerboard array of binaries. You know, even at this location, I can still say, can I use the K and K prime value to encode information, right? That still remains a valid thinking. But now I move to I have, you know, if I want to use the value degrees of freedom for information coding, I've also now imposed a regular spatial, checkerboard array to address the value at this value degrees for within this supercell or that supercell and another supercell. So my ability to encode information densely have enhanced.
Oh, you also have different supercells, and you can kind of study entanglement between different supercells.
In principle, yes.
Oh, I see. So twisting, adding adds to the picture entanglement between different supercells.
Yes.
Of Moiré superlattices.
Correct. Originally, I had to deal with the whole D layer, but now I impose a supercell. I just had a natural way to define a dense, bits, if you will.
Oh, I see. As supercells.
Yes, supercell.
Thank
you. No more questions, Elaine.
Okay. So I'm just getting started, to air some grievance that actually is not easy to control them individually, especially optically, because I cannot focus my laser down easily to address individual supercell. But, the first step is to recognize when does the supercell influence my optical spectrum. Okay. So this is the optical experiment. Basically, these, let's focus on the blue lines. So these are the intra-layer exciton electron hole pair in the same layer. And this is the interlayer exciton electron hole pair in different layer. The energy spacing between the two is largely determined by the band alignment shift between the two monolayers. And compared two samples, these are the blue are taken on a sample with HBN encapsulation. And the dotted line is unencapsulated sample. You can already see the dotted line, we just have very broad exciton resonances that are probably broadened because, the Moiré superlattice quality is not very good. There's a lot of variations. What we did here, like many other people in the field, is to use this high gap, atomically flat HBN hexagonal boron nitride to encapsulate the sample, improve the quality. But we're still left very puzzled by what are these multiple peaks, right? It could be just, there's some uncontrolled strain, as we now have worried about, that are shifting the position of the excitons. So it took us a long time to build any confidence to assign them to quantized exciton states. Okay, so after a dozen samples later, we're only going to show you our best samples and best spectrons. Okay, so this is a spectron taken from 1 degree sample, and this is taken from 2 degree sample. This is a focus on the interlayer exciton, the low energy excitons. And then we measure this sample. We have multiple transition. We measure them on many different spots on the sample. And there are some fluctuation in the positions, in the resonant energy. And the resonant energy spacing is on the order of 20 MeV. Okay. And now for the 2 degree twist angle, energy spacing seems to get bigger. So again, if you allow me to use a super simplified model, is that created these quantum boxes. When I make the twist angle larger, the box size are getting smaller. We all learn in quantum mechanics, as you have a quantum well, one-dimensional quantum well, for example, you make it narrower, the energy spacing is going to get larger. So this is the first hint that these transitions are likely quantized by the Moiré potential trap. And another clue is that, if we excite the 1 degree twist angle, 1 degree sample with sigma plus light, we analyze the polarization emission, we find them have an alternating preferred PL. why they're both sigma plus and sigma minus emissions that come from the two value I have talked about, K and K prime value. They're degenerate. But we create the electron hole pair in one valley preferentially if the lifetime and the valley scattering are on a comparable time scale, then I can retain a little bit of valley polarization. So the fact they're alternating is only true for 1 degree sample, and there are more elaborate calculations recently to show that these selection rule can go through some modifications. They're just detailed consideration. You need to see whether you have alternating selection. Okay, so there's a lot of detail there, but that just again is another clue that tell us that could be related to the Moiré supercell, the Moiré superlattice. We also debated why should the exciton created stay at different spatial location in the Moiré supercell. There's alternative pictures. So if you imagine, here's the Moiré potential landscape observed by the exciton. If it's deep enough, I can actually have a 1s-like exciton, the ground state exciton. I also can have higher excited state excitons. These excited state excitons are known in quantum dot literatures, right? People have reported as like, P like D like kind of hidden symmetry states in the quantum well. So can these ground state and excited state also lead to changing selection rule? The answer is yes. These are calculations done by a very simple parabolic band, and these are calculated central mass wave function. And you're sampling the local atomic aligned by layers differently. And if you calculate the absorption spectrum, they will have this alternating selection rule. But absorption spectrum is easy to calculate, but hard to measure. What we measure is photoluminescence. People like Vernon would appreciate, photoluminescence is not ideal to figure out the selection rule, because photoluminescence is a dynamic process, count on the competition of many relaxation channels. So we can only say it was a hint that we rely on to assign those peaks to the Moiré excitons. So I just presented another picture to you that even if I have exciton that also always localized near the AA site, if I can have ground state and excited states, they would also give me opposite selection rules. Okay, so again, let me pause and say if see if there are questions.
So Elaine, there's one question. Florian has a question. He says, within the quantum box model, the lowest energy state should be most affected by increasing confinement. However, the lowest energy state is constant under twist angle. Why is that?
Well, constant under twist angle in the sense of their energy?
Yeah, exactly.
Okay, so first of all, I would say we didn't fit all the details in our spectrum. Okay, so you can see there's a little bit of blip on this peak as well. I would also say we're not 100% confident that each of these resonances all have the same origin. What I'm trying to say is typically people know their defect states in these materials tied together with the vacancies. So is it possible one of the peak is actually defect bound state? It's possible. I cannot rule them out with 100% confidence. Okay, so we basically, write the paper with the simplest model just to kind of get people to start to think about how Moiré potential can change the optical spectrum. So there are a lot of details that are continue being debated. Okay, so I see I'm running short on time. I just want to show you a little bit what our most recent work is that, in fact, whether they're localized or delocalized is potentially tunable. So to confirm that, we actually compared CVD grown sample, this time also MOSE2 and WSE2. When you grow them, because the lattice constant is so close, you just form a commensurate heterostructure with a type 2 band alignment without any Moiré superlattice. And when you stack them, again, it's hard to avoid that. We try to do imaging experiment. Are exciton moving in these materials? The answer is when you don't have the Moiré, they move over rather long distance. The lifetime of these excitons, these are also interlayer exciton. The lifetime is on the order of nanoseconds, okay? And they can move until they hit the boundary of the CVD grown flakes. But when we have 1 degree twisted angle sample, we do not see diffusion beyond the optical diffraction limit. That changes when we have a 3 degree twist angle. So this is 2 sample, these pictures are spatial dimension and energy. So they're more confined in the lateral dimension in the 1 degree sample than the 3 degree sample. The change is I twist the sample, make the quantum boxes smaller. There's a more opportunity for the excitons to hop around to, or another important reason is they live longer. In the 3 degree sample, we know, here's another separate study. We know that in 1 degree sample, the lifetime is comparable to the sample without twist. But as soon as we twist them to 3.5, the lifetime had changed by more than a factor of 10. You can continue with this trend. You get very long lifetime with this interlayer exciton. And there's a couple mechanisms for that. One is actually when I twist the layers in the real space, I'm actually also twisting their band structure in the momentum space. I have introduced a little bit of indirect transition nature to the interlayer exciton that has a huge effect on the lifetime. Okay, so I just want to say it's very difficult to be 100% confident that your optical spectrum is caused by the Moiré potential because of lack of spatial resolution. So because of that, we look for other supporting evidence, like is their property tunable by the twist angle? For example, this is one piece that we confirmed lifetime and diffusion are all dependent on the twist angle. And there's someone who asked about AB domain separated by AA domain boundaries. It's much more prominent in what we call the homobilayer, where we know if we take a monolayer and tear piece of it out, and then we can control the twist angle really well. And there's lattice reconstructions. These layers do not act like Lego pieces. They would deform because interlayer coupling and strain that Veron asked about. Strain turned out to be maximized at around 3 degrees. And we know there's basically a Moiré pattern changes. The superlattice lattice reconstruction changes around 2.7 degrees. And there are 3 routines of lattice reconstruction. These are calculations, and people know lattice can reconstruct, but what's hard for the calculation to figure out is where is the angle that reconstruction happens. We determine that through simple far field Raman measurement. Okay, so again, in the interest of time, I'm not gonna go through the details of these spectrons, but just to say, in the case, we can actually, when the twist angle is small, this is less than 0.1, there are many ways to directly map out the Moiré superlattice. This is a map out of the Moiré superlattice in our own sample. And then because of lattice reconstruction, the Raman spectrum, if you can measure them locally, will be different because there are actually lattice distortions in this reconstructed superlattice. So again, I'm happy to answer a question after I let everybody go. I don't want to extend far more than an hour, but I do want to spend my final few minutes talk about quantum information applications. These are speculated. So instead of creating single photon emitters in solids based on defect states, modified molecular modification, or self-assembled dots, we can hypothesize to create a regular array of single photon emitters using Moiré supercell. And not only that, I can imagine localized individual electron hole and really build a platform that I can have a spin-based technology and then use photon to address individual spins. So when you dope the Moiré superlattice with a certain control doping level, you can populate only the first Moiré Moiré mini bands. That effectively puts one hole each Moiré cell. So I literally created a model system to solve models like Fermi-Haber model, which is not analytically solvable, right? So the area of quantum simulator has largely been occupied by our colleagues that are working with trap ion systems or array of cold atom systems. And the benefit they enjoy is they can address individual supercell, and because they're separated by about 500 nanometers, they're created optically, and then you can separate them, you can individually address them. But one can hypothesize that now with a regular array of confined electron hole or exciton, we can reclaim some of that quantum simulation area and use Moiré crystals as intermediate quantum simulators to emulate a lot of phenomena that we've been studied in solid state, but in a different regime, a different platform. So, I just want to leave you with these two pictures and say that we know how to confine an array of individual holes. And there's every reason to believe they can act as single photon emitters. We're not at the point of addressing them individually, but before we get there, there are also interesting quantum simulation problems I can already do. So with that, I want to end my talk 1 minute past the hour and be happy to answer more questions.
Thank you, Elaine. Questions? Alex?
Sorry.
You have a question?
Well, in order to use it as a simulator, you have to be able to make these excitons hop from one valve to the other, or
Right.
At least interact via spin interactions, something dipolar.
Right. So,
are any of those things possible? Or?
So first of all, I think that it is possible ultimately to control the individual supercells optically. And you can think about techniques that people have been developing with super resolution imaging. You can actually get down to 50 nanometer resolutions. And there are already people doing, scanning near field spectroscopy with the hope to resolve them individually. But I think there's a way to do it completely optically, okay, without scanning probe. And another thing is, I didn't have time to show some of the literature in this area. There are groups that are claiming they have already seen evidence of quantum simulators where they're actually using the optical transition to probe the ground state. So the idea is you have, let's say you dope the material, you have an array of a hole, right? You form perhaps a Wigner crystal state you form a rigid electron or hole lattice. And then you excite electron hole pair. And there's clear coupling between this optical excitation with those ground states. And then there are already people starting to infer either they have antiferromagnetic-like interaction or not in this array of holes. So I would say this effort to construct, to experimentally demonstrate quantum simulators is already on the way. But I certainly expect a lot more to be discovered. All of these are actually done in exactly what you said in the classical limit, where they actually do not allow electron hopping between different supercells yet. So then you can ask, once you allow that hopping parameter T in the Haber model, what else they can see. So that's completely unanswered at this moment.
Also, the domain sizes, they're big enough that they don't create intervalley scattering, right?
I think we have very little knowledge about how intervalley scattering is happening in this. Frankly, in the bilayer, there are going to be a lot of valley that are relevant, and because once you start to fold the bands, you just it gets more complicated. I don't know the answer to your question really, how intervalley scattering influence these experiments. I would say if they think about a ground state and they're just occupying one of the bands. I don't know how they're spin polarized because if the time reversal symmetry is retained, you have another copy.
Yes.
But I think most of these experiments are done in high magnetic field. They kind of lift that degeneracy to make things a little easier to understand.
Okay.
So Elaine, I had a question about the lattice structures that so, given the fact that we can't really probe optically anything at that lattice scale of the Moiré, but given what we can do optically, if you looked at just PL, do you see anything like, say, super radiance or anything that is collective here that is coming out of this? I mean, what we can do within the optics domain?
Yeah, I think if you just have the bare Moiré,
yeah,
I'm not sure super radiance will naturally occur. It might, because you think about the photon wavelength is large, right,
yeah,
compared to the supercell.
yes.
And so, I think, the exact lattice, like I said, it's better controlled in the twisted homo bilayer. But when we study these homo bilayers, we just see a lot of peaks, that we have trouble to interpret. So we needed to make better control devices to start tuning them to get more hint where they're coming from. I would say same is true for all the literature that exists on homo bilayers right now. So I think they're not, the interpretation is not very specific at all at the moment. And we also don't have evidence of whether they are localized or delocalized. Sometimes you have these big, huge Moiré cell, right? Because they're easier to image. But are they the best to construct the quantum dot-like state? Is unclear. They become quasi 2D. But when you make them smaller, let's say 10 nanometer could be ideal packed quantum emitters. But then, I think we lose some, anyway, so we think it's possible. Actually, for Dickey state, that sort of thing, potentially is the best because you actually know how many emitters you might have, right? We're certainly hoping to be able to see something like that, so far without success.
Okay. Any other questions?
Yeah,
Oleg has a question. Oleg, go ahead. You can ask the question.
Oh, thank you.
Yeah.
What are the possible symmetries for Moiré superlattices for excitons in twisted TMDC bilayers?
So, some of them have the rotational symmetry, right? And then if there's not many magnetic defects, then you have the time reversal symmetry. That
Sorry,
what do you mean by symmetry?
I mean like square lattice or triangle lattice. Or
I understand. Right.
Which one?
So the most commonly studied starts with hexagonal lattice, but there's certainly material that will give you a square lattice. I just haven't seen a lot of high quality optical spectroscopy work with square lattice yet.
But in materials you study, you have a hexagonal.
Yes, start with hexagonal lattice.
For excitons,
Yes.
Moiré.
Correct. Yes.
Thank you.
So, Elaine, in this tip enhanced Raman, what's the spatial resolution?
Right. This is not our work. The spatial resolution. They also image the huge Moiré supercell, and they did it in graphene. Okay, this is bilayer graphene. So I don't remember the spatial resolution off the top of my head, but probably around the order of 50 nanometer. So what they did is they would have such huge Moiré supercell, and they just park their tip near the apex or on the domain walls or in the center. So, and then what they could see is additional peak or splitting that emerge in the Moiré. That's the way we infer the lattice reconstruction as well. It's really amazing that the Raman spectrons are very sensitive. even though, here below the 2 degree, 2.5 degree, the Raman doesn't move because there's no atomic alignment change. Although the Moiré supercell is changing, the atomic alignment is not changing, so it doesn't move. But then you enter what's called the transition region. There's a continuous evolution for the atomic alignment. Then both the Raman energy and line width or splitting are continuously evolving until you hit what we call the rigid lattice region, where the two layers are mostly decoupled. Then the Raman doesn't change again with twist angle. So I should say, obviously we're not the first people to do Raman experiment on twisted bilayers, except for early experiments have too big of a step size in the twist angle. So they would do 0 degree, 5 degree, 10 degree, and then 20 degree. So they missed these subtle variations in the spectrum, where our actual lot of lattice reconstruction related to Moiré pattern is happening very quickly.
So the two blue areas are where things are kind of like the regular crystal, and then the region in between in the shaded pastel is where all the reconstruction is happening.
Yeah, so it's easier to talk with the calculated spectrum.
Yes,
Okay.
yeah.
So, for example, in the reconstructed, what we call the relaxed region, the blue region, are complete commensurate stacking. In fact, in this case, there's no gradual atomic alignment change. Okay. And then the AA stacking is on the domain wall. And the particular atomic stacking, there's no gradual changes, just a flat quantum box separated by rigid walls. Okay. And then you have these transition region where the region between the for the domain wall and the inside the domain start to get blurry. Okay. So then you start to have a gradual variations of atomic alignment. I don't want to give you the impression anything else I told you earlier is wrong, is because this lattice reconstruction is more relevant for the homobilayer. In heterobilayer, it still occur, but over a smaller twist angle. There we don't have a very good control. The heterobilayer, you don't control the relative angle that well. You're counting, you align them using microscope image. You're just counting to get lucky, to keep them within 1 degree, right? You think you can keep them half a degree, you're very happy. You don't have that fine control. Yeah. And also for heterobilayer, homobilayer, the interlayer coupling and the strain works differently. So you don't expect, the lattice reconstruction to persist over such a large twist angle. But, I would say the homobilayer, if in principle, is a great way to, perhaps even better for the quantum emitter array, because the selection rule can be simpler. You don't have to worry about the spatial variations, right? And except for we're not there to get a really good control over the optical spectrons and things like that yet.
Cool. Thanks, Elaine. Any other questions?
So the bottom line is you're looking for, you would prefer the excitons to be well localized.
Yes.
That's your aim, right?
Yes.
And then your box picture would work. Right?
Exactly. Yeah. If you want if I want emitters, or if I don't want to do quantum simulator, I just want to encode my information in individual holes, then I want to these isolated, localized holes or excitons.
But they should live long enough, so you need fairly large twists.